Hey, everybody. So I'm going to go through several examples here. You can see them up here. These first three, we're looking at functions defined by an infinite series. And we want to find the domain. So we'll talk about what that means in just a second. And then we're going to look at a Taylor series for a particular function. We'll spend a little more time on that one, I think. So when we define a function by a series, and we talk about the domain, we mean the same thing that we mean when we talk about any function's domain. Well, I shouldn't say any time, because so when we talk about domains in general, there's typically two things that determine the domain. The one we're not caring about right now is the real world application. Sometimes the real world says these are the only inputs that matter to us for a variety of reasons, right? If you're starting a process, setting a ball on a hill and rolling it downhill, you can come up with a function that describes where it's at a certain time. Well, that only makes sense for positive values of t because the ball was doing something different before you started your stopwatch or something like that. But in terms of the mathematics, when we talk about the domain, we're asking what numbers is this function defined for, right? So something like 1 over x has a domain of everything except 0 because at 0, it's not defined. We mean the same thing here. When we talk about a series, when is it defined is when it's convergent. When is it not defined? When it diverges, right? If it has a sum, that's the definition of it, right? That gives us an output value for that function. So looking at this first one, for instance, f of x, we're saying if I put in different values of x, some of them it may converge for, some it won't. So if I put in a value, let's take an easy one, 0, every term is 0 here. That means the input 0 has the output 0. And so that's an easy one to do in this case, right? But what happens at the number 1 or the number 17? We don't know. And so we don't know which of those inputs yet has an output defined for it. So the way we do that is checking for convergence, which we can do with our convergence test. All right. So I'm going to choose convergence tests for each of these. I'm just looking at the series right now. You may have chosen a different convergence test. There's often more than one way to do it. I'm going to do what I think is going to be the most straightforward and easiest, but I could be wrong. You might have found an easier path to this. In my mind, this is a good one for the ratio test. It's probably the one I pick most often. If there's not some easy, like looking at this for test for divergence, these terms certainly go to 0. That n in the denominator will eventually should beat everything. So let's take a look. Well, I guess that will depend too. That one might work for some numbers. Anyways, I'm going to do the ratio test. So what I need to look at is the n plus 1th term. In this case, x to the n plus 1 over root of n plus 1. The nth term, of course, is just what's written there. When I take the ratio of these two, so a to the n plus 1 over a to the n, what do I get? I'll get x to the n plus 1 over root n plus 1 times root n over x to the n, which can all be worked out to be x times the square root of n over n plus 1, right? So a little bit of algebra, we get this. So then we're going to take our limit as n goes to infinity of the absolute value of this thing. As far as this limit's concerned, x is some value. We put in a value for x. N is the thing that's changing. So x is a constant as far as this limit's concerned. So I can pull out the absolute value of x. There should be absolute values around this, but since n is positive, we're taking the positive square root. This works out. This limit, so I'm going to spare some details on this limit. This limit is 1. I like to think intuitively as n gets very, very large, that plus 1 doesn't do much, right? A billion over a billion and 1 is really close to 1. Taking the square root makes it even closer. So this limit turns out to be the absolute value of x. So when does the limit, the ratio test tell us that a series converges? It tells us it converges if its limit is if the limit of this configuration is less than 1, in other words, this converges when the absolute value of x is less than 1, or x is between -1 and 1. However, at the endpoints, the test is inconclusive, so we don't know yet what happens at the endpoints, but we can test the endpoints individually, right? So let's see, when x equals 1, our series looks like 1 over the square root of n. And you might recognize this as a p-series. It's 1 over n to the 1/2 power. And this diverges by a p-series test. Right, I'll just put here, let's say p is less than 1, right? That's the p-series test. The exponent has to be greater than 1. So it doesn't converge at x equals 1. How about at x equals -1? We get something a bit different. We get an alternating series. I'll write it this way this time. And remember the alternating series test. If we look at the absolute value of these terms, they do go to 0. 1 over the square root of n, as n gets larger, goes to 0. So we have an alternating series whose terms go to 0. This converges. I'll just put by the alternating series test. So now that tells me exactly what happens. The domain, right, we get between -1 and 1, but we can include -1. So it is converges at one side, one end of the domain, but not at the other side. Okay. All right. That's our first example. Now we've got g of x. I'm going to use exactly the same test, the ratio test, which will look like this. No, sorry, I apologize. That's the wrong one to choose. See, what I'm noticing, I'll finish what I was first thinking, but I realize now this is the wrong idea. It might work, but it looks difficult. This is kind of a weird configuration to make. You want things to cancel there, and they don't quite cancel. And we probably have some intuition about what happens between those two, but it's not really clear what's going to happen. So I think this was a bad idea. I'm gonna jump to something else. Let's do, this is a perfect one for the root test, right? Whenever you have both, whenever your terms, right, I could rewrite the terms like this, right, using the rules of exponents. And that root test now looks very, very nice because the nth root of the absolute value of the nth term will just look like this, right? So that nth root gets rid of that nth power, and so it greatly simplifies this, right? Okay, so with that in mind, now I take the limit. I'm taking the limit, x minus 2 over n. Again, I can think of taking this constant out. It's weird to think of x as a constant, right? The idea is what we're doing is letting n change. So we're thinking x is a variable, can take on each number, but for any number, what happens when we do this limit? And when for any number x, when we put it in, it's a constant, we get the limit as 1 over n times the absolute value of x minus 2. This limit is 0. That limit becomes 0. Okay? And so what that tells us is, first of all, this tells us it converges because the limit is less than 1. And notice x doesn't show up, meaning it wouldn't matter what value of x we put in, right? Look at this limit. If I put in a trillion minus 2 divided by n, eventually n gets bigger than a trillion, and then it's bigger than 10 trillion, and then a trillion. And so that fraction is always going to 0, which tells me that the domain here is all real numbers. Okay, so our first one, we had a small interval. Here we have all real numbers. All right, one more of these kind. Again, this time, because of that factorial, I'm going to do the ratio test. All right, the root test with factorials doesn't work very well. I don't know how to, playing between roots and factorials is tricky, integrals, all that kind of stuff. We don't have a lot of tools with that, but the root test, the ratio test works very well for these. So let's just get a look at the ratio first. It's going to be n plus 1 factorial, 3x minus 2 to the n over n factorial, 3x minus 2 to the n, oops, this should be plus 1, which gives me, so n plus 1 over n plus 1 factorial over n factorial is just n plus 1. And we get all the factors canceling except for the one in the numerator. The limit of this thing in absolute value. Whoops, let's erase that. All right, so we've got n plus 1 times 3x minus 2. We can factor out this if we want. N plus 1, and this will go off to infinity, right? So in other words, what we're saying is no matter what value we put in for x, even if we put in something that makes that thing very, very small, as n gets larger and larger, it eventually goes to infinity, right? In other words, we got to think about what that means, though. What it means is the terms keep getting bigger. So if I put in a number, like if x is 0.5, I get 1.5 minus 2 is -1/2, an absolute value that's 1/2. It's a small number, but n's eventually going to get huge. So that's those numbers, we can make them as large as we want. There's one case where that doesn't work out. And that's the case if x equals 2/3, because then 3x minus 2 is equal to 0, right? You can do that quick bit of algebra. Which means if x is equal to 2/3, h of 2/3 is just n equals 1 to infinity of n factorial of 0 to the n, which is just 0 plus 0 plus 0 plus 0. So in this case, so this is not saying, I want to be very careful here, this is not saying 0 times infinity is 0. 0 times infinity, when that shows up in limits, is indeterminate. You don't know what's happening because we got an infinity here, and now I'm showing you there's a 0 and somehow it gets rid of that. But that's not what's happening. What is happening is for each term, when n equals 1, we get 0 times 1 factorial. Then we get 0 times 2 factorial. Then we get 0 times 3 factorial. Then we get 0 times 4 factorial, and on and on and on. So at no point are we multiplying 0 times infinity. What we are doing is multiplying 0 times numbers, and each of those numbers gives us 0. And so the series that just adds up 0 over and over and over again is just gives us 0. Okay, so that's what happens here. So in this case, our domain is just one number. What did I say? 2/3. Okay, there's one place where this thing converges. This entire function can be written down as 2/3 sends us to 0, right? Remember, a function is just a pairing between inputs and outputs. This silly function just has one input, 2/3, and one output, 0. That's the only thing this function does. For every other number you try to give this function, it says, I don't know what to do with that number. I can't do anything with it. So it's kind of a useless function. But it demonstrates what something we've said about these series. When we have power series, these three cases show us everything that can happen. They either converge over an interval, centered an interval. The endpoints can converge or not converge, or they can converge for all numbers, or they can converge for exactly one. So for our power series, this is what always happens. Okay, and so if you get something else, like over two different intervals, then you know something is not quite correct. Okay, or that you get it converges nowhere. It'd be very easy to do this test and forget to check for the 0. But every power series, right? If I put in x equals 2 here, I get zeros. if I put in x equals 0 at this first one, I get a bunch of zeros. So you can always find that 0 that makes each term 0 and it converges. But otherwise, then you either get an interval or all the rest of the numbers or none of them. So those are the three cases. Okay, let's move on to the Taylor series. Sorry for that glitch. I realized my coffee was tragically left in the other room and I couldn't do a whole nother problem without it. Okay, so we're going to do this Taylor series. Let me just give us a little space. Let's see if this works. Just felt crowded up there. All right. So we want to compute just the first 4 terms of this Taylor series. There we go. First 4 terms of this Taylor series. So let's just write ourselves a little note about what that actually means. So remember, if I'm writing a Taylor series for k of x, what I'm saying is we'll have some constant plus a constant times x minus a. In this case, I'm giving, sorry, I should have said that we're doing the Taylor series at x equals 11. So that where it's located, we get x minus that plus another constant times x minus 11 squared plus another constant times x minus 11 cubed. Of course, the Taylor series goes on, but these are the first 4 terms. These are the things that we want in this case. Okay, so the trick is most of the work is done. Every time you're talking about a Taylor series, this is what we want, right? You have to be given a place to do it. So the a value, in this case the 11, it's always going to be a constant times a linear factor, a constant times a quadratic factor, a constant times a cubic factor, and on and on and on. The trick is coming up with these coefficients, but the coefficients are very well defined. The nth coefficient is just going to be the nth derivative of my function evaluated at a, in this case, that's 11, divided by n factorial, okay? Right, so that just means the nth derivative, right? The 0th derivative is just the function itself, the first derivative, the second derivative, and on and on and on. So that's really our job, is to compute derivatives and evaluate them. Everything else is just plugging in numbers, okay? So the process of finding a Taylor series is really the process of taking derivatives and evaluating. So let's go ahead and do that. So so let's just write down several of our derivatives. So our function is 3 minus x to the 1/3. Let's do it horizontally. I always do this vertically, but I don't quite know why. K prime of x, well, I get 1/3 times 3 minus x to the negative 2/3. But then I have a chain rule. I got to multiply by -1, so I get a negative right here. Then k double prime of x, I'm going to get negative 2/3 times negative 1/3 gives me 2/9 times 3 minus x to the negative 5/3. But again, I'm going to get a negative popping out. And then k triple prime of x, I'll get negative 5/3 times negative 2/9 gives me 10/27. 3 minus x to the negative 8/3. And there's my negative from the negative x on the inside. Okay. All right. And I'm going to do one more thing here just to make, we're about to have to compute these, but I noticed that each of them, I'm just going to use the rules of exponents and rewrite this in what might be a funny way. So here, let me just do the first one in detail up here and you'll see what I'm doing. 3 minus x to the negative 2/3 is the same as 3 minus x, what did I want to do? Oh yeah, negative 1/3 times 2, right? That's just rules of exponent, or that's just rules of fractions, which now I'm using rules of exponents. This is 3 minus x to the negative 1/3 squared. There's rules of exponents. And one more thing, 3 minus, oops, I didn't do what I wanted to do. That negative 1/3 can be written as, that negative 1/3 exponent means I can rewrite this as 3 minus x to the 1/3, and that squared is out there. Okay. The same thing can happen for all of these. They just have a different numerator. Here it was a 2. I've got a 5 and an 8. Why am I doing this? Because notice what's sitting right there is the function itself is now in the denominator. And when I'm going to evaluate these, I'll already know what that number is. So it'll save us a little time later, I think. You can debate whether or not you think this was worth the time. This one will become k double prime of x negative 2/9 1 over 3 minus x to the 1/3 to the 5th. Again, you don't have to do this step. All we're doing is computing numbers in a second. So however you want to compute these is fine. To my mind, this is a slightly easier way to compute it. I mean, you can also plug it into a calculator. You're probably going to get ugly or decimals, which I don't really feel like writing down. I'm just going to use the fractions. Let's see, to the 1/3 to the 8th. Okay, so remember what our goal is. I am trying to compute these coefficients, right? So right now, I've got my nth derivatives. I just have to evaluate them at 11. So let's just go through and evaluate each of these at 11. K of 11 is 3 minus x to the 1/3. Oops, is 3 minus 11 to the 1/3, which is negative 8 to the 1/3. So the cube root of negative 8 is negative 2. Okay, so now notice, now we see why I did this work a minute ago. That 3 minus x to the 1/3 is a negative 2. That denominator in all of these fractions, this negative 2 can replace just the denominator. So in other words, each of these parentheses becomes negative 1/2. So let's go ahead and do that. So k prime of 11 becomes negative 1/3 times negative 1/2 squared, which is going to be negative 1/12. Okay, so there's one of my derivatives. K double prime of 11 is negative 2/9, negative 1/2 to the 5th. So what are we going to get? We'll have a pot. Let's see. This is going to be negative because we're taking a negative to the 5th power, and then we've got a negative out front. So we'll have a positive. In my numerator, I have a 2. In my denominator, I have a 2 to the 5th, but I can cancel one of those. So I have a 2 to the 4th, and I've still got a 9. So 2 to the 4th is 16. Did I do that right? 90, and I don't remember the numbers I got. Oh yeah, that's right. I'm sorry, I'm thinking a step ahead, and this wasn't the right number, but that's because we haven't finished yet. So far, so good. So this is what? 90 times 10 is 90, plus 9 times 6 is 54, so 144. All right, and then negative 10 over 27 times negative 1/2 to the 8th. All right, this one's a bit uglier. So we're going to get negative 10. We're going to get a positive from the 8th power, and we'll have 2 to the 8th. I can cancel a factor of 2 with the numerator, but I don't think I can do any more of this in my head. So this is 27 times 2 to the 7th. Well, let's see. What was 2 to the 5th is 32, 64, 128. I'm just going to leave that like that for now. We can compute these numbers when we're all done. All right. So we're almost there. Now remember, what we need to do in each of these cases, we just take, to get the coefficient, we take the corresponding derivative, divide by n factorial. In other words, C0 is the 0th derivative, which we just computed as negative 2. And actually, because of the fractions, let me just write one other thing I'm going to do. I'm just going to rewrite how we can do this. We can also just take, whoops, let's write it differently. I just started copying what I had. This is just a little bit of algebra. I can take the nth derivative at 11 times 1 over n factorial, right? I'm just doing this to show you what I'm about to do is just each of these fractions is going to be multiplied by 1 over n factorial, right? That's just what, these are just equivalent statements. So C naught is -2 times 1 over 0 factorial. Remember, 0 factorial is 1, right? Probably seems a little weird. It's important to keep it that way. It's true. We're going to always use that. So the first one is just -2. K prime, oops, not K prime. What am I doing? C1 is equal to -1/12 times 1 over 1 factorial, which again is just 1. So this one is -1/12. C2 is 1 over 144 times 1 over 2 factorial. 1 over 2 factorial is just 1/2. So this is just 1 over 288. And then C3 is this whole thing, -5 over 27 times 128 times 1 over 3 factorial. So that's a 6. We're going to jump to a calculator in a minute. These numbers, these are our 3 coefficients. Okay, these are them. In other words, now we can finish this off. The first 4, let's write it this way. The third degree Taylor polynomial. So I'm calling it third degree. There's 4 terms, but the degree is the power on the highest power on x, and here we see a 3, is going to be -2. So I'm just following this map that I have up here, right? There's my constant term, -1/12. So now this term times a linear term in x. Then plus C2, which was 1 over 288, x minus 11 squared. And then we get minus 5 over 27 times 128 times 1 over 3 factorial. So again, I'm just being lazy and not computing this right now, but that's just a number, right? Whatever number that is, 5 over 27 times 128 times 6, whatever ugly number that is just a number. And so we take that and we multiply it by a cubic term. And there is the Taylor polynomial. Sorry, the third degree Taylor polynomial, or in other words, the first 4 terms of the Taylor series for this function, okay? So it takes some work, but all I did was follow the map, the program, right? This just tells me what to do. We derived it. It's a really fascinating derivation. You just match derivatives, but it spits out something kind of nice, right? This part's really simple. We just write down factors in x, right? X minus wherever we want it to be located with coefficients. And then the coefficients have a very simple formula. The hard part is taking derivatives. So here was just the first derivative over 1 factorial, the second derivative over 2 factorial, the third derivative over 3 factorial, and so on. And so we just do each piece at a time. Now, let's take a look at the graph of this function. So let me share something different with you. Here I have it graphed on Desmos, and let me just go through, for those of you who hated having that number there without having that number there, that 5 over 27 times whatever that was, 128 times 6, that works out to 20,736. So that's, if you're desperate to know what that computed to, that's what's down there. But here's what I really want to show us, okay? Make this a little bigger. The blue line is the function. That is the cube root of 3 minus x. That's our function, okay? At x equals 11, the value of that function is -2. So I've put that point on the graph, okay? And let me do one more thing. Let's just copy down what we just had. So our our Taylor polynomial was -2 minus 1/12. Keep missing that. 1/12 x minus 11 plus 1/288 x minus 11 squared minus 5/20. Let me look again, sorry. Can't quite remember what that was. 20,000 something, 76. 736, okay. 736, let's hide this again. We're gonna graph this in just a second, but I wanna make a couple comments. Right now, what you're seeing graphed is just the function y equals -2. That's what that red dotted line is, okay? So think about what that is. That is the simplest function that has the minimum condition that it matches the original function at the point we care about. So for us, that's 11 -2. So this is the simplest function I can come up with that matches this function at that point. It's an approximation to this function, right? If you're looking at this function near this point, they're not terribly far away for some small interval. But we can see pretty quickly that it's not a good approximation for very long. In Calc 1, you learn to find the tangent line approximation. There's the tangent line to this function. That is this portion of the Taylor polynomial. It's the first two terms, the constant term and the linear term, right? If you remember the tangent line approximation, sometimes at x equals a, sometimes it's written as f of a plus f prime of a times x minus a. That's exactly the first two terms of the Taylor series. The constant is the value of the function at the place you're looking for. The derivative divided by 1 factorial, which is of course 1 times x minus a. That's just the first two terms of the Taylor series. That's our tangent line approximation. This is now a function that not only matches the original function at this point, right? They both go through this point, but their first derivatives are also the same, right? So it now is a better approximation. We see how much closer it is to the function near there. If we zoom in, they're laying nearly on top of each other right around that point, right? So by, the constant approximation just matches the value there and nothing else. Then we match the value and the first derivative. As we add terms to our Taylor series, so now I'll add the third term, the quadratic term, right? Look at what happened. Here's the linear approximation. That quadratic now bends it so it matches a bit better. The linear approximation is the one disappearing and coming back. That quadratic bends in, right? So now it matches the value of the function, the same first derivative. They would have the same tangent line there. That tangent line we just drew would be the tangent line for both of these. And it matches the second derivative. We added concavity to the equation. It now not just goes in the same direction there, it's bent the same way. So we get a slightly better approximation. You can already guess what's going to happen at the third. Now, when we add this fourth term, the third degree, the cubic term, we get a slightly better approximation, right? It bends it more tightly. We've matched another derivative. And this is what the Taylor series does. It just keeps matching derivatives, which gives us a tighter and tighter fit to the original function, right? So this is now this third degree Taylor approximation to this function, right? So the 0th degree approximation is just the value of the function. The first degree is the tangent line that you learned about in Calc 1. And we continue going with better and better approximations by matching more derivatives. So that's the big idea here. And what happens is the more derivatives you match, that in general, your approximation gets better. I haven't talked about this in my videos, and I'm not going to cover that in this course, but there are error functions. The more derivatives you match, you can minimize your error over, you can find out the maximum error you could have over different intervals. And so depending on what you're doing, you can decide, a scientist will decide how good of approximation they might need using these error functions or error approximations. And so they might only need a linear approximation, or they might be doing some precision work and they need a 10th degree approximation, right? These can be used in computing and calculators. If your calculator spits out 10 digits, you don't need more accuracy than to those digits, right? And so you can program it to compute something like an exponential or a sine function using a series like this, and you know how many terms you need to go to get a good approximation. Okay, that is it for this one. I hope that helps. Thanks, everybody. I will see you next time.